Okay, so we had in isomerism, we had discussed structural isomerism or structural isomers. In the structural isomers, we had discussed carbon chain isomers, positional isomers, functional group isomers, and now we have to discuss tautomers or tautomerism. Tautomers or tautomerism. So what is tautomerism? It is a special case of functional group isomerism. It is a special case of functional group isomerism, a dynamic equilibrium between two molecules, a dynamic equilibrium between two functional group isomers exist. So this is a special case quite often of functional group isomerism, in which there is a dynamic equilibrium between the two isomers, such as they coexist at the same time in an equilibrium situation. At the same time in an equilibrium situation. Like we have two molecules here. The molecular formula is C3H6O. It exists in two isomeric forms. One is ketone form in equilibrium. It exists in equilibrium. One is ketone, the other one is enol. Enol, alkene and alcohol, enol. Ketone and enol. So we'll discuss this example. See here. Tautomers, the keto-enol interchange. It is a functional group isomer of C3H6O. C3H6O. But it exists in equilibrium. This molecule, these two molecules, they exist in equilibrium. This is a classic example based on functional group isomers involving a dynamic equilibrium. So this ketone is in equilibrium with the enolic form. So this ketone, which is propanol, is in equilibrium with prop 1 in 2-ol. Prop 1 in 2-ol, a bifunctional alkene alcohol, or sometimes referred to as an enol. So that is why it is known as keto-enol equilibrium. Understood? Keto-enol. Ketone, enol means alkene and alcohol. So it is an example of tautomerism or tautomer. It is an example of tautomerism or tautomer. So what is tautomer? It is a special case of functional group isomers or functional group isomerism, in which there is a dynamic equilibrium between two functional group isomers. Understood? We'll take a few more examples. 2-hydroxyketone and alkene diol. 2-hydroxyketone. This is 2-hydroxyketone, and this is alkene diol. This R is alkyl group. It may be aryl group also. For example, C6H5, CH3, C6H4, etc. So the hydroxyketones with aryl groups tend to form the alkene diol more readily because of resonance, delocalization, stabilization. So this is another example. So we'll go with only one example, this one. Keto-enol interchange. This example is best example. Propanon and propene 1, prop 1 in 2-ol. Prop 1 in 2-ol. Propanon and prop 1 in 2-ol. It exists in keto-enol form. So it is an example of tautomer, or it is known as tautomerism. Understood? Now we have finished discussing this structural isomers. Now we'll discuss stereoisomers. Stereoisomers. So first we'll discuss the definition of stereoisomers. Then we'll go to other page. Okay. So what are stereoisomers? Stereoisomers, one is configurational isomers and the other one is configurational isomers and conformational isomers. Configurational isomer and conformational isomer. Stereoisomers are classified into two groups. One is conformational isomer, the other one is configurational isomer. The other one is configurational isomer. Conformational isomer, configurational isomers. So first we need to know what are stereoisomers. So stereoisomers have both the same molecular formula. Both the molecules will have same molecular formula. They have the same molecular formula and structural formula. Molecular formula as well as structural formula. Both are same. Same structural formula. It means they are connected in the same way. But they differ in the spatial arrangement of atoms in the molecule. But they differ in the spatial arrangement of the atoms in the molecule. Only the spatial arrangement of atoms or group of atoms is different in these molecules. Understood? They have same molecular formula, they have same structural formula, but they differ in the spatial arrangement of the atoms in the molecule. So we'll discuss this, okay, using different using slide, okay. So again, we'll discuss this stereoisomers. Okay. So what I have told you, stereoisomers, they have same molecular formula, they have same molecular formula, the same structural formula, but the only difference is the arrangement of atoms in space is different. Spatial arrangement of atoms is different. Okay. Isomers which have the same molecular formula but differ in the manner their atoms or group of atoms are arranged in the space are called stereoisomers. There are two types. One is conformational isomer or conformational isomerism. The other one is configurational isomerism. The first, it is classified into two different categories. One is conformational isomers, conformational. The other one is configurational isomer. So first, conformational isomers. Conformational isomers. Conformational isomers. The stereoisomers which can be interconverted rapidly at room temperature. The stereoisomers which can be interconverted rapidly at room temperature without breaking a covalent bond. Without breaking a covalent bond are called conformational isomers or conformers. Conformational isomers or conformers. The stereoisomers which can be interconverted from one form to the other form. The stereoisomers which can be interconverted rapidly at room temperature without breaking a covalent bond. There is no breakage of covalent bond. So without breaking a covalent bond are called conformational isomers or conformers, because such isomers can be readily interconverted. They cannot be separated under normal conditions. Because such isomers can be readily interconverted, they cannot be separated under normal conditions. Under normal conditions, separation of these molecules is very difficult. Understood? Now the second one, configurational isomers or configurational isomerism. See the different, just a slight difference in the word conformational and configurational, configuration and conformation. So this configurational isomers, the stereoisomers which cannot be interconverted, unless a covalent bond is broken, are called configurational isomers. So there is a double bonding between two carbon atoms. There is a double bond or triple bond between two carbon atoms. Okay. So the stereoisomers which cannot be interconverted unless a covalent bond is broken are called configurational isomers. The configurational isomers is again of two types. They are again classified or categorized in two types. One is optical isomer or optical isomerism or enantiomerism. We have discussed yesterday what are enantiomers. Then second one is geometrical isomerism or geometric isomers. Geometrical isomerism or geometric isomers. What are geometric isomers? Geometric isomers, EZ isomers, E or Z isomers, or cis or trans isomers. They are geometric isomers. EZ isomers or cis and trans isomers. They are geometric isomers. Optical isomers or enantiomers we had discussed yesterday. See, now we'll discuss optical isomers or enantiomers. Again, optical isomers, the name itself, optical isomers. The stereoisomers which are related to each other as an object and its non-superimposable mirror image are called optical isomers or enantiomers. Optical isomers are enantiomers. So what are enantiomers? Enantiomers are non-superimposable mirror images. Enantiomers are non-superimposable mirror images. Enantiomers are non-superimposable mirror images. The optical isomers can also rotate the plane of polarized light. That is why they are also known as optical isomers. So the optical isomers can also rotate the plane of polarized light to an equal degree, but in opposite direction. To an equal degree, but in opposite direction. If one molecule is rotating left, the other one will rotate right, but to an equal degree. The property of rotating plane of polarized light is known as optical activity. Optical activity. The property of rotating plane of polarized light is known as optical activity. Optical activity we will learn later on. Okay. Now we'll take one example of lactic acid. One is minus, the other one is plus. They are enantiomers. This is an enantiomer. See, it's this molecule. This one is the mirror image of this molecule, but they are not this molecule is not superimposable on its mirror image. It is not superimposable on its mirror image. The molecular formula is same, C3H6O3. It has two enantiomeric forms, two enantiomeric lactic acids. It represents two enantiomeric lactic acids. This molecule, this one is the mirror image of this initial molecule. But this initial molecule is not superimposable on its mirror image. So they are known as enantiomers. They are known as enantiomers. One is negative lactic acid, the other one is positive lactic acid. This one, the negative lactic acid, it rotates the plane of polarized light towards left hand side or anti-clockwise. It rotates the plane of polarized light to anti-clockwise. Okay. Whereas the other one, the image one, it rotates the plane of polarized light towards the right hand side. It is clockwise. It rotates the plane polarized clockwise. The initial one, it rotates the plane polarized light to anti-clockwise. Anti-clockwise. So we have this example as enantiomers. So what are enantiomers? They are mirror images which are non-superimposable. Mirror images but non-superimposable. Understood? Now the second class, the geometrical isomers or the geometric isomerism. Geometric isomers are the stereoisomers. Geometric isomers are the stereoisomers which differ in their spatial geometry. Differ in spatial geometry. See, we have two carbon, double bonded carbon, but these atoms, they are arranged in different manner in two molecules. Same molecular formula. We have same molecular formula, but the arrangement of these atoms is different in both of these molecules. See? So what are geometric isomers? Geometric isomers are the stereoisomers which differ in their spatial geometry due to restricted rotation across a double bond. Due to restricted rotation across a double bond. It cannot be rotated. This across this bond, because of this double bond, this rotation is restricted. It cannot rotate. This cannot be rotated. These two cannot rotate. Okay. There is restricted rotation across a double bond because of this double bond. So these isomers are also called as Sis Trans Isomers. These isomers are also called as Sis Trans Isomers. Sis Trans Isomers. So if these two first priority molecules, they are on same side, then it is known as cis configuration. Cis configuration. So this is cis 1,2-dichloroethane. Cis 1,2-dichloroethane. And if they are across the same molecules, same atoms, if they are present across the same double bond, carbon double bond, they are known as trans isomer. So this is trans 1,2-dichloroethane. Trans, chlorine here and the one is here, the other one is there. So it is they are present to the trans position. So that is why trans 1,2-dichloroethane. Trans 1,2-dichloroethane. So these isomers are also called as cis trans isomers. For example, molecular formula C2H2Cl2 corresponds to two geometric isomers. So C2H2Cl2, it has two geometric isomers. It has two geometric isomers. Understood? So what are geometric isomers? So geometric isomers are the stereoisomers which differ in their spatial geometry due to restricted rotation across a double bond. Due to restricted rotation across a double bond. We have these two molecules. The molecular formula is C2H2Cl2. It has two isomeric form. It has two isomers. Okay, one is this, the other one is this. See that arrangement of atoms in a space in this molecule is different than this one. So this, for the first one, chlorine molecule, chlorine atoms, they are present on the same side, and hydrogen atoms, they are present on the same side across a double bond. So because of this, it is cis 1,2-dichloroethane. In the other molecule, the chlorine atom is present across the double bond. The chlorine atoms, they are present across the double bond. That is why it is trans 1,2-dichloroethane. Trans 1,2-dichloroethane. Understood? Trans 1,2-dichloroethane. Okay, types of optical activity we'll discuss tomorrow. Types of optical activity or optical activity we will discuss tomorrow. Optical activity. Understood? Now, if you have any question, we can discuss. Robin, Rose, if you have any question, we can discuss. Niharika. Optical activity we will discuss tomorrow. Next class.
Sir, in optical isomers,
Optical isomers, there are two optical isomers, enantiomers. Optical
okay,
isomers, enantiomers and diastereomers. Optical
okay,
isomers,
in
enantiomers
geometry,
and
yes, sir.
diastereomers.
Yes, sir.
Okay.
In geometrical isomers, we have 6 and trans isomers, no, sir?
Cis and trans in geometric isomers.
Okay, sir. Yes, sir.
Understood? So
Yes,
in stereoisomers, there are it is classified into two categories. One is conformational isomer, the other one is configurational isomers. In configurational isomers, again there are two types. One is optical isomer or enantiomers. The other one is geometric isomer. Understood? Hello? Hello?
yes, sir. Understood, sir.
Okay. Geometric isomers and optical isomers. What are optical isomers? They are able to rotate the plane polarized light. They're able to rotate the plane of polarized light. Optical isomers, they are able to rotate the plane of polarized light. Understood?
Yes, sir.
Conformational isomers and configurational isomers. Stereoisomers, they are classified into two categories. Conformational isomers and configurational isomers.
Configuration.
Configurational isomers, again, they are classified into two categories. Optical and geometric isomers. Optical and geometric isomers.
Geometrical.
Understood?
Yes, sir.
Rest we'll discuss tomorrow. Optical activity, we'll discuss optical activity tomorrow. Robin,
Yes,
do you have any question? Robin?
No, sir.
Did you understand?
Yes, sir.
Stereoisomers. Two, it is classified into two categories. Conformational and configurational.
Configuration?
Conformational and configurational.
Yes, sir.
See, we have not discussed any example of conformational isomers. This conformational isomers we'll discuss later on.
Okay, sir.
Okay.
Okay. Like I'll show you conformational isomers. See this. These are the conformational isomers of N-butane. See, eclipsed, gauche, partial eclipsed, anti or trans, partial eclipsed, gauche. This is very important topic in for exam also. So we'll discuss. These are conformational isomers of N-butane. These are conformational isomers of N-butane. And what happens in this case? The two carbon atoms are bonded, singly bonded. There is a single bond between two carbon atoms. So the rear carbon and the front carbon, they can easily be rotated. In conformational isomers, the atoms, they can easily be rotated across the two carbon atoms. So that is why they are conformational isomers. Understood? We have this conformational isomers of N-butane. Eclipsed form, gauche form, partially eclipsed, anti or trans, partially eclipsed, then again gauche. As they get rotated, we get different isomeric forms, different conformations of N-butane.
The conformation.
Hello?
Sir, is also important topic, sir.
This is very important for 5 marks. Conformations of N-butane.
Okay, sir. Okay. Okay, sir.
So rest we'll discuss tomorrow, okay?
Okay, sir.